All right, hey guys, we are ready to start section 3 of chapter 5, and section 3 has to do with angle bisectors. So we need to remember what that concept is. An angle bisector is a ray or line that bisects an angle, that cuts an angle exactly in half. So it creates two congruent angles. And so our angle bisector theorem here says that if a point is on that angle bisector, typically a ray, so if there's a point on that ray, then it is equidistant from the two sides of the angle. So let's take a look at a diagram that would represent that. So if we're looking at this picture here, we have angle BAC and we have AD bisecting that angle. And we can see that because the two angles are marked with the hash marks to show them congruent. And so what this theorem says is that if there's some point D on that angle bisector, then that point must be the same distance to one side of the angle as it is to the other side of the angle. Now we got to look back a little bit and remember what we defined back in section 1, wasn't it?
Yeah.
Section 1. Am I remembering right?
Yep.
Of what it means to have the distance from a point to a line. Remember, the distance from a point to a line is the shortest distance. And so that shortest distance is always a perpendicular distance. Actually, you know what? That was in the last section of chapter 3.
That's right.
So we're going back a ways to remember that. So if we're looking at the shortest distance from D to AB, it has to be the perpendicular distance, BD. And we know that's perpendicular because it's marked with a right angle. If we're looking at the distance from point D to AC, then we're looking at the shortest distance, which is the perpendicular distance, DC. And again, we know that's perpendicular because it's marked with a right angle. And so those distances, those lengths from D to B and D to C must be equal if D is on that angle bisector. That's what this theorem says. Okay, so if D is on the angle bisector, then it has to be the same distance to one side of the angle as it is to the other side of the angle. That's the angle bisector theorem. So let's apply that here with this picture. So we have an algebraic equation that we need to set up here because one of those distances is represented by 5x. The other distance is represented by 42 minus x. And so because our theorem here says that those are equidistant, because D is on the angle bisector, we would set those equal to each other. And so we would go 5x equals 42 minus x, add x to both sides, we get 6x equals 42. And so if we solve that, divide both sides by the 6, we're going to get x is equal to 7. And that would represent the correct value to plug into that to make that a true statement. All right, that's the angle bisector theorem.
All right. So now, just like with almost, okay, so now we're going on to the second theorem we're going to have here. And just like we had the converses for like alternate interior angles or alternate exterior angles, we also have the converse of the bisector theorem. Remember guys, converse is you switch the subject and the predicate, and so now the initial statement is the conclusion and the conclusion is now the hypothesis. So the converse of the angle bisector theorem says that if a point is equidistant from the sides of an angle, then it lies on the angle bisector. So it kind of looks, well, let's take a look at what that's saying here, okay? Oops, let me just fix this here so we can just kind of get a quick visual of what it is it's saying. So if we come here and we make an angle, hopefully that'll straighten out for me, there we go, and then I come in and I just put a point right here. Okay, now let's say I put that point right there, and then if I draw a line through that point, okay, oh, let me erase that and fix that here real quick. Forgot to use my little line tool here. So if I draw a point or a line through that point there, and then I straighten it out. Now, if that point is equidistant, now remember what Mr. Scritchfield just said about that equidistant had to be on a perpendicular, meaning, let me change colors here, that if I draw a perpendicular from the outside in, and then now I'm stating that's a perpendicular there, and then I draw another one from the outside in, and then, oops, that didn't look very good. Let me get rid of that. And I draw another one that's perpendicular. It's not going to be perfect, but I'll put the package in there so now we know it's perfect. So now, what that's saying is that if that's equidistance, meaning that if I come in here and I can put my hash marks to show that those two distances are the same, then this point right here is definitely on this bisector right there, okay? So, what that theorem says, let me just run through it here again, is if this point right here in the middle, this little red point, is equidistant from this side and this side from the perpendicular, then we can conclude that that point lies on this bisector. Okay, so let's kind of put this into application because you might be a little bit confused here. So let me clear all this out. All right, so we're gonna look at some pictures here, and this one says, can you conclude that ray EH bisects angle FEG? So let's look at some pictures here. So on this one right here, does EH bisect angle FEG? Now I just want you to think for a minute, okay, and try to think about what are the things that we know have to happen here in order for this to work. And there's really two things you can kind of look at here to deduce that this doesn't work. So hope we've had a chance to look at that, and you should have realized that this is no. Now let's talk about why. All right, Mr. Scritchell, what's one of the reasons when you first looked at this why you said that this was a no?
Well, there's only one right angle in there, first of all, and it's not in the right place. The right angle must be between the side of the angle and the line that's showing the distance out to the point. So in this diagram, it's that blue line. And so that blue line and the side of the angle have to be perpendicular to each other because that's what the distance is. And neither one of them are, and so that's not a distance. That's not the distance that we're talking about.
And the other one that I would point out would be that we do not know that FH is congruent to, what is that,
G, I believe.
HG down there at the bottom. So if those two things aren't congruent, then that also leads me to believe that that is not a perpendicular bisector because, as Mr. Scritchell said, the angle is going from the inside, from the ray on the inside towards the outside of the angle instead of on the outside of the angle towards the bisector in the middle. So that one is definitely a no. Now let's look at another example here. Oops, still on that. Okay, so let's get this thing going for it. Now this one here, if you look at the differences between the first picture and then this picture right here, you can definitely probably see a little bit clearer what Mr. Scritchell and I were talking about a few moments ago, in the fact that this one is definitely a yes. And let's look at why. So if we look at this here, okay, we can see that we have a right angle here on the outside, and we have a right angle here on the outside of the angle, and then we're measuring to that point H. Remember, it's from the segment to that point has to be on a perpendicular, not the other way around. So you can see, and then you can also see that HG is congruent to FH, and those are the two things that we need to know for certain in order to prove that EH is indeed the angle bisector of angle FEG. So biggest differences between this picture and the previous one was, once again, the right angle's on the outside going in towards the point, and then those two segments are indeed congruent. Anything else you want to add, Mr. Scritchell?
No, that's the big difference between those two diagrams. That's what we need.
All right. So there you go.
Okay, our last slide, I believe, for today. And this one relates back to the last section, the last slide actually of the last section, where we're talking about concurrency again. So just a reminder, concurrent lines are three or more lines that intersect in one point. And so we just have a little different one. In the last section we talked that we would have three of these. Well, here's the second one. So we have concurrency of angle bisectors now of a triangle. And so now what we want to do is we want to look at the three angles of a triangle, create those bisectors. So we're going to bisect every corner or every angle within the triangle and see where those bisectors hit each other. And they actually intersect at a single point, so they are concurrent. And that point now is called the incenter Last one was the circumcenter, if you'll remember. This one is now called the incenter. And that incenter, in this diagram, point P, is equidistant from the sides now. It was the other way around before. It was equidistant to the angles. But now we have the angle bisectors, and now that point is equidistant to the sides. And so it's similar to the angle bisector theorem that we were just talking about. And again, the difference between circumcenter is that the circle that gets created is going to be on the outside of the triangle, compared to the incenter like this. Now if we draw a circle with a center of P and create the radius that hits those points, it's going to hit at the sides being tangent to the circle. Not necessarily a term we've talked about yet, but to where the sides of the triangle are tangent to the circle, that means they just hit it at one point, okay, and to where that circle is inside of the triangle. And so it's inscribed in the triangle, therefore that's why it's called the incenter. Okay? And all those blue diagrams that Mr. Bedell is marking right now, blue segments I mean, are perpendicular to show the distance again, shortest distance, and they're all congruent to each other. So that point, that concurrent point of all the angle bisectors is the same distance to all three sides.
You remember what that one that was down there, Mr. Scritchfield?
I don't.
We'll call it A.
Okay, so all three of those perpendicular segments are congruent. All right, and I think that's it for this section.
And guys, don't be too overly concerned if you're struggling a little bit with in-center and circumcenter and all these things. We're going to spend a lot of time trying to really give you guys a chance to just really delve into this and kind of get some real world understanding of what these things mean. So just take the notes, try to gain some understanding, try to really learn about angle bisectors more than anything else, and have a good understanding of what those mean. And you're moving along in the right track. All right? Yeah,
we're hoping that we can, this is one of the sections that makes this process that we're doing here, where you're watching the video and doing other activities in class, where we can find some activities that will make this cement up for you and make sense. So be patient with it. Okay, guys, thanks. We'll see you in class.